I gave a similar talk last year, and this talk is going to kind of extend on that. Because the talk is 1 hour, I'm going to separate it kind of in 2 parts. And initially, it was in 2 parts to begin with, but right now, it's the parts I'm going to do. And let's see. The first part is I'm going to use this mind map because in this kind of comparison, it's a little bit too chaotic to switch between, to do it only in one, only say in presentation in R and only presentation in Mathematica. So in the first half an hour, I'm going to summarize some of the key points in the last year's presentation. We're going to look into simple functionalities which are missing in Mathematica from my perspective, but they're present in R. I think an important part is to discuss graphics. How well do you see this? And the other thing is that I would like to give one illustrative example about the differences. Hopefully, if I have time in this half an hour, I'll make the responses. I'll start some of the responses to observations I have seen in the talks this year. Obviously, that can be a lengthy list. But basically, the first 4 branches here, hopefully, we'll do in the first half an hour, and you can attend another meeting. There's a GitHub repository with this comparison. It's called Mathematica versus R. Unfortunately, GitHub is down. So during lunchtime, I was informed that this is the case. So if I click, say, this, it's basically nothing is happening. So anyway, I do have preloaded some of these notebooks here. So in principle, yeah, well, I'm not going to dwell on this. In principle, when you can go to the GitHub page, Mathematica versus R, and it has an opening page and a nice breakdown of the different functionalities there. And let me be a little bit more specific. Like you'll be able to see, I hope, something like this. And maybe and so this let's zoom a little bit. There's a table in this in the GitHub repository which actually says what exactly is the breakdown envisioned of the different functionalities to be compared between Mathematica and our projects. So here, some example in this table. You can see some example projects. Like we are going to look into this 100 indigence classification by matrix factorization, and you can see what is saying classification. It is data ingestion. It's about images. It uses latent semantic analysis, matrix factorization, and it's using parallel computations. So you can see this in the first row. And similarly for the other projects. All right, so so this, as I said, it's a good idea to kind of to summarize what was discussed last year on this topic. And I'm going to it. It should be somewhere here. Really hope so. All right. So this is from last year, 2015. Mathematica and R, they come from the same family. They're descendants of the Lisp family. They're very similar. They're both universal languages. We're going to see mostly here applications in statistics and predictions and classification and so forth. But you can do other stuff with R. Same with Mathematica. Mathematica is really more diversified into doing different stuff, not so specialized as R in doing statistics. The ideologies, though, are quite different. R is a functional language obviously, but it's also with lazy evaluation. And it's based on objects. I mean, Mathematica also has objects, but not in such an explicit way, at least in my opinion. The data structures in R are very different. It does help to have taken at least one course or two in statistics in order to understand why R is doing things in this way. It's basically following the mindset of statisticians. In my previous talk in this conference, I stated that I'm suspicious of statisticians. I'm even more suspicious after starting to use R. So R has all the features of a design by committee in a bad way. There are like 20 statisticians who designed it. Most of the features work most of the time, but that's just not good. And now Mathematica is made by physicists and a computer scientist, and mainly by Steven, who is a physicist. And Steven is curating Mathematica as a language, so basically it's much more consistent. With R, very often after you learn certain rule or you think you got it, there's some exceptions, which actually you need to learn the exceptions of the general rule. This I find very frustrating. The only excuse for R to be like this is that it has been designed 30, 40 years ago, long time ago. And that's why, for example, you have these short names in the functions and so forth. So it has certain legacy, which, okay, I mean, it can be accepted to a point. Could have been improved? Yes. It is very important to learn about data frames. Let me see here. DataFrame is the major data structure in R. It's not the most fundamental one, but it is the central one in many ways. So you need to know how to manipulate data frames, produce data frames, query them, and so forth. The granularity in R is to a vector, so there's no scalars. So the finest granularity you have in R is a list of numbers, or list of whatever, list of objects of the same type. This not necessarily bad, not necessarily good. I understand why you have done it. As I said, if you take the statistical mindset, you're like, yeah, you don't use colors. We use only vectors and tables and whatnot. All right, so lists and vectors, they can take named elements. So in some sense, they are very similar to Mathematica's associations. A relatively new data structure is the sparse matrix. So R doesn't have sparse arrays. It has sparse matrices. This is really nice. The sparse matrix functionality is really nice. There are some new data structures like data table, and I don't know, data table is probably going to replace DataFrame. It is a little bit, the introduction of data table into R, it is very analogous to introduction of data set in Mathematica. It's kind of the same, but also kind of different. And it does make our practitioners to use this kind of data in a different way, not so much like before with data frames. A central object is, another object is formulas. We'll see probably some applications of formulas. In a sense, if you want to become intermediate R user, you need to use formulas. Factors are extremely annoying. I try to avoid them as much as possible. This is, again, the statistical thinking. Anything which is not a number, we're going to convert to integer. This is what factors are doing. There's some very subtle, very interesting bugs that can be produced in this way. As I said, I avoid using it. The only reason I have not specified in my options, startup options of R, factors never to be used, is because when I give code to some other people, they're not going to have this option set. So in a sense, I wouldn't know what is happening on their side. So all right, this is enough with this. The good features about R. I had it somewhere here. There are certain unbeatable features. It's like almost impossible to compete. And so great IDE support. Like RStudio is impressive product. Emacs Peak Statistics is a very old program. It's very nice. IntelliJ IDEA, which many people use, I use it. I use it for Mathematica, for Java. For R, not so much, but yeah, it has support. Somebody wrote a plugin for IntelliJ. One of the best features of R is the package system. So with the package system, you have access to lots of packages. This is just the package system itself. Now, the other thing is the actual packages. If you need something and you're wondering how to get your hands on it, somebody wrote a package for it probably, and you can find it and use it. When you write documents, which is another important thing, it is important to be able to integrate with other people, other systems, and R actually does a great job. Documentation integration with LaTeX, Markdown, and HTML is really great. You can use it in several ways. We also utilize an open source program called Pandoc. Pandoc allows you to convert from different formats in a reliable way. Something very similar to the dynamic features of Mathematica is Shiny, the Shiny library. So this actually is even, in some sense, better, and I'll show why. It is still under active development, so it hasn't reached the maturity of the dynamic functionalities in Mathematica. But you do have interactive interfaces in R, and this can be very, very useful. All right, so this was what was last year, and I'll probably expand it too much on it, but it is important to mention this. So back to this mind map. So the simple functionalities which I think we should have, Mathematica should have, but doesn't. And they have equivalent in R, and I'm going to show some. Like, for example, this is here one example of, this is a Markdown notebook. This is not officially released yet, but RStudio, and what you see is RStudio. It's a front end to R. It does support notebooks format, which is in the Markdown, based on Markdown. So here I have, I'm loading some data, and I'm making this command summary. So this summary command is going to tell me what this empty cars is, it's having these columns, MPG, cylinders, whatever, horsepower, and they have these values and so forth. So I can also go further and with this command, draw these cross correlations between the different variables. So in some cases, we can see we have some correlation, etc. So in Mathematica, there is no, this command like pairs and summary, there are no commands like that. And summary is probably one of the most used commands in R. It's extremely useful to summarize the data in one way or the other. So the corresponding commands in Mathematica would be something like this, and let me, I was positioned on it. So let me zoom here. I'm not going to use the empty cars example. I'm going to use the Titanic data because, well, I'm familiar with it. So basically, this loads the Titanic data. You can see with this command, record summary, I have computed the summary. This is something I implemented, this record summary. It basically gives me the summary of the data there. And I have another command which I can call this variable dependence grid, which can give me some kind of summarization of what's going on in this data. So what is similar to another thing is cross tabulation. Again, let me see. It's very natural when you have this kind of records of data, right? Table, some kind of data table, to kind of we want to know what are the co-occurrences between, say, how many females have been in the first class, how many males have been in the first class, and so forth. So this is a generalization on cross-tabulate. It's cross-tensorate. It works actually in higher dimensions. And this is something R is doing. When I mentioned this formula object, this is basically what is happening. You can specify the column names here from Titanic, passenger class, passenger age, passenger sex, and survival. So basically, you can say, look, I want to see the counts of, these contingency values of these columns. And so if you do that, again, oh, sorry, I should have typed matrix form. I mean, we can see the breakdown of the different groups. And this is another example here, which is instead of using counts, you can use the last column, like you can see in the summary here. The passenger age is not a categorical variable; it is numerical. So basically, instead of doing the just counting, which I did say here in cross tabulate, I can actually add the ages. So this is basically the summary age of the people in the different classes. So all right, I mean, this is something, again, like this is something obviously very useful. It's even if you test classifiers and etc. I saw several examples here. People from the machine learning group in Mathematica, they need to kind of do it manually. This here, it's a mosaic plot. A mosaic plots are ingrained in also, like there's several libraries that do mosaic plots in R. This here gives you a breakdown. I mean, this is a visual breakdown of the information we saw above. So you can see that there are different, different classes, like different. I mean, we start from the passenger class, and then we see, the breakdown in male and female, and then in the survival. These tables here, they give you the conditional probabilities for each of those. So this is something already in R. It doesn't look as pretty, it doesn't look as functional, but has been there for quite a while, and people use it quite often. This is not in Mathematica. As I said, I find it very useful, especially if you explore new data. It's something to do. All right, so R graphics. Well, that I didn't expand on this. We had three graphics systems. The base system, lattice, and ggplot. Actually, ggplot 2, and base. So this is one of the more frustrating things for me. I cannot use one of these graphic systems when I work with R. I need to basically know all three of them to some degree in order to do to solve practical problems. And ggplot is very nice. It's written by one of the most active contributors in the R community. He also works he's a senior scientist, senior developer in RStudio. I know that lots of people in the graphics department in Wolfram are aware of the designs behind ggplot, and they should. The base one is very old. I mean, because it's very quick to use, that's why I use it, but in general, I don't like it. Lattice is based on a system called Trellis. This system is long 30, 40 years ago. If you'll probably see some examples. Again, I'm really, in the workflow in R, you don't have such direct manipulation as in Mathematica of the graphics objects. So you need to actually manipulate your data frames in certain ways. And then after you have manipulated your data frames in certain ways, you can feed them to the plotting functions. This sounds abstract, but I'm going to show it in the illustrative example of the differences, which is the next branch. Here, to make something, to make a good example of something really hard to do in R. Hopefully this is going to work. Yes. All right, so this is a blog post I did like probably a month ago or two. So you have some data like this, and you want to remove, this is a free data, you want to remove outliers. And so actually, you can see this is the full data, but if you zoom to it, it's very clearly some outliers. What I do is I'm basically making some envelopes around this data using, it's basically the data, I'm finding the center of the data, and I'm rotating it in different angles, and I'm finding basically 98%, which plane divides the points to 98% below and above. So if I do this in sufficiently many directions, I'm going to produce some kind of, I can produce some kind of surface envelope like this. Now, what is nice about it is that you can actually, this function quantile envelope region, it is using region member, it is using the region functions. It's actually fairly efficient, fairly quick to do. And here are the actual outliers. The reason I'm showing this example is that, yeah, this is very relevant to when you do data analysis and etc. R doesn't have 3D graphics. They all live in this 2D world, so, you know. And it's very bleak, in my opinion, but whatever. So this, using the 3D graphics and having finer access to the graphics primitives, in many ways, in my opinion, is really useful. All right, so the example I was talking about of the differences, it's this one. I'm going to extract it here. So, yeah, let me see. I mean, as far as I know, GitHub is not, it's not accessible, so I'm not going to deal with it. So we're going to, right. Well, let me see something here. Is it going to work out? OK, good. All right, so here, we have seen enough, especially, you know, for time series data, you might have seen enough, several talks of how we are accessing time series data for weather time series. This is one of the things with R, and why I have chosen this example as being illustrative. You need to, there's no standard package for getting this kind of data. I mean, you need to basically get this package weather data, which is well reputed, well known. It's maintained by one person. He commits, you know, reliably on GitHub. But basically, this is it. After that, you need to, yeah, we need to kind of download this package, read the manual, how to use it. You cannot just specify, say, Atlanta, Georgia, which is what I want. You need to actually find the stations in Atlanta, Georgia, and then from these stations in Atlanta, Georgia, to actually get the weather data. In order to use the ggplot, which I'm going to show later, the commands with it, as I said, you need to be able to reshape your data into particular form which is used by the graphics. That's why if you use ggplot2, you need to use reshape2. It's like impossible not to use it otherwise. I'm a big fan of quantile regression. And this package here, quantile reg, it's one of the most important contributors in quantile regression. We're going to see that it's a very different philosophy when you use this kind of fittings with R. So here, basically, we're just reading the data. I mean, from whatever. I basically found the station. I also realized that I cannot exactly query for a range of dates which exceed 1 year. So you need to kind of actually make this kind of loop which kind of goes through the years and so forth. So finally, at some point, we do get the data, and then we can produce this kind of time series plot. So when I'm fitting the quantiles, I'm using this package, but you see this is the formula I'm talking about. And this is the RQ. I mean, what I said, like you use, OK, RQ is for regression quantiles. Actually, that's a widely known name, but just looking at RQ, of course, you cannot guess it. And this comes from the times in which people have been making small commands when you deal with computers and programming languages. The infix operator you see here, it's actually a matrix multiplication. This is what is happening. If you stay for the second part of the talk, I'll be talking more about infix operations and how you can define and redefine operators in R. It's very similar to what we do in Mathematica. It is actually quite nice in a sense. What we see here, the do call part, in which I need to combine all these curves in order to plot them into and put them into a data frame. The do call part is actually apply. So I'm applying this function cbind on these curves, and then they get concatenated. Basically, the curves, they're not curves, they're just vectors at this point. As I said, this line with x multiplying fit coefficients, it's a matrix vector multiplication. So we produce, we have basically produced vectors corresponding to the quantile curves, and now we want to put them together as columns in a table, and this table is called DataFrame. And then with this DataFrame, we're going to be plotting stuff. And in order to plot it and have this kind of colorful plots, I actually need to use ggplot and some melt function and whatnot, and then produce this plot. If you know, I mean, it's pretty dramatic. If you have done it a few times, some people claim it becomes automatic. I don't think so, but whatever. You can see here that, again, there's some kind of variables. You can specify which variables have been used, in what way, why is this happening, and so forth. This is the ggplot command, which I said is very nice. We are basically saying we're going to work on this data frame. We're going to be making lines, and these lines, the x-axis is going to be dates, the y-axis is going to be temperatures, and then we're making some other lines with the fitted quantiles. The first one here comes from the time series. And finally, we're going to have a point part, which is for the outliers, the points in red. So, I mean, again, it might seem quite foreign right now, but actually, it is quite interpretable. It's quite nice. It's structured quite nicely. If you have done it a couple of times, you actually can maintain this kind of code. All right. So what was interesting for me is that from here, when I have this kind of quantiles, if I specify a time point in time, like say this white line here, I would like to reconstruct what is the PDF and the CDF at this point. And you can see this is one of the reasons to use quantile regression. The signal is very heteroscedastic. This means that, let's look at it in the original form here. The variance is depending on time. So you can see that during the summer, the temperature is much more, it has much smaller variance. And during the winter, Atlanta is a southern state. There is no winter like in Champaign. Actually, whatever. But it's not as cold not as cold as, it doesn't get usually as cold as here. But you do have this wide variation. You don't know from the day before, you cannot exactly predict what is going to be the temperature in the next day. So because of this, it might be an important, obviously from any kind of perspective, like machine learning, statistical data mining, whatever, you might want to be able to reconstruct the PDF and CDF at different time points. And so this is what is happening here in this example. And in order to do that, I need to use some function approx_fun, but this didn't work actually that well. Basically, you don't have a reliable interpolate function in R. There is something, but you cannot use it in the same way you use it in Mathematica. You need to do some kind of manual stuff, and you see this is what I'm doing with this PDF estimate function or whatever. If you decide to use spline functions, then yes, you can integrate it. You can differentiate it. It's going to be smooth, but actually doesn't fit. The CDF and the PDF doesn't look as nicely or as informative if you use linear interpolation. So this here can be completely compared with, let me see here. I did started with this time series part here. So if you see the Mathematica part, hopefully we can, or not. Well, while I'm waiting for this to load, we're going to look into what I showed you earlier with this opening page. There's some statement here about what are these projects doing. The projects organized, in general, the mission statement behind this repository is to collect simple but not trivial projects of doing different machine learning and statistical tasks, like something like this with the quantile regression. It's like, I mean, it has been also a question for me if I want to do all this part which I know how to do in Mathematica, all this, how I do it in R. So this is not exactly a Rosetta Stone type of collection of commands between Mathematica and R. You need to know a fair amount of Mathematica or fair amount of R at least. But you can also like see what is the correspondence. I usually keep like at least 95 correspondence between the codes. Sometimes it just doesn't make any sense to keep 100% correspondence because the languages are different. I mean, but the logic between the exposition is kind of the same. And let me see this if this Mathematica PDF. No, it didn't. Well, I mean, it's not a big deal, I guess. I can go to projects. I can go to the time series with quantile regression and show you this file, which, if you look at this file, it's basically following, as I said, it's following exactly and more or less the same points, and you fit the quantiles and you make the extractions of the PDFs and CDFs. But you can, in a sense, side by side, you can actually look at these codes and see what is going on. All right, so this was well, let me see in my mind map. I wanted to make a couple of points here. So you see, since I assume you know Mathematica at least to a point, and you're less familiar with R, I would like to point out several things. It is really important to be able to work with data frames, to be able to create, manipulate, and reshape and whatnot data frames. There is no way around it, so to speak. You need to master it. And the general workflow in R is very often, as I said, it's very statistically motivated. Like say statisticians like to use design matrices and so forth. So yeah, this is what was happening. For these quantile regressions, I didn't actually produce, like in Mathematica, what I'll do, I'll use the B-spline basis, which are just functions, and I'll use some weights, and this is how I'll do the linear programming, etc. My Mathematica implementation just takes the nodes and takes the nodes on which this B-spline basis is going to be. In R, you actually need to provide the design matrix for the B-splines. And this is something they consider normal, where basically it is such an idiom for, I mean, theoretical idiom for the statisticians, but you're going through it. And so the last point, which I already mentioned, you need to gather your functionalities, meaning you need to figure out which packages you're going to use. There are some packages which are more maintained, they're used more often, and so forth. It's not like in Mathematica, more or less, you can fairly well query the help system and find how to do, say, weather forecasting or weather data retrieval and whatnot. You might have several options in R which can provide very different outputs from what you're doing. And you are at the mercy of the developer, but they have done it, they have documented how to do that. Usually this is enforced by the repository for submitting R packages. You are supposed to write a vignette, which basically is a use case type of document which tells you how to use whatever. And I think in this particular document, which I've been looking at, we looked at, there should be a link to the vignette by Roger Kuenker, which I hope it's working. I mean, this is basically, he explains here how to use quantile regression in R. And he has like different use cases. Basically, this is what I read. I read this document. This is how I learned how to use this quantreg package and so forth. Right. Okay, well, so, I mean, I went over for this half an hour, which I promised I'll do but this is basically the first part of the exposition I wanted to do. It is very interesting to look at some of the functionalities which parallel the functionalities we saw in earlier in the conference, or functionality which was actually promised, like Spark, for example. Now, let's look at the first two, actually, the R scripts and Spark. I'm talking about this branch here now. So this R scripts, they have been around forever. You can use scripting. It's fairly straightforward. You just say R script, whatever R program, and it's going to be executed. I use it fairly often, and it is indispensable to communicate ideas, especially with customers or engineers. Like very often, I'll do interactive interfaces, which would kind of, if I want everyone to get on board, engineers and stakeholders, I'll do that. Actually, this is too abstract. I kind of mentioned something like that for when we are discussing the brain networks from time series. So let me actually go to, let me show you one of these, how it is done. So here I have this, so basically I have a R session. This is an R session, and I have this R file, like R code file, which basically loads the libraries, loads the session which was saved, and that does some initialization, and then it calls the dynamic interface. What is happening is I'm going to do R script on this. So this is going to initialize the whole thing, and it's going to produce an URL. This URL is produced by the library Shiny, and I'm going to show it here. This is basically running locally on my computer. This is an interface to a dynamic interface. Not sure how well it looks like, but if you don't believe me, actually, I mean, you can believe me, but basically, this is actually a bipartite graph. It's one of the questions I had to the presenter with the brain networks. And so you can see that I have two types of nodes, movies and actors. And if I, for example, move to this action, adventure, drama, and and tweak some of the parameters here, I'm going to have slightly different recommendations. Now Star Trek becomes the most important movie, and William Shatner becomes the most important actor, and so forth. And you can look at different parts of how it looks like, how things look like. Like, for example, the Pareto distribution of the ranks and so forth. As I said, I can actually package this into one zip file, upload it to, say, Google Drive, whatever, give it to customers, engineers. They can have a interactively kind of experiment with the ideas I'm proposing, not use much, statistical language, hand waving, and then, after everyone agrees on what we are doing, we proceed doing it. This is indispensable. Mathematica has similar promise of doing things. You can deploy on the web and stuff like that. You can use CDF. I have tried all that. With R, it's really when it worked. With the other solutions, they were not so good. All right, so Sparka, I do have a code for Sparka, actually, which I would like to share. But let me see in my document here. Again, this might be. All right, this is very nice. Like, in some interviews or job interviews or whatever, they might ask me, like, oh, have you used Hadoop or Spark? And like, this question was important 5 years ago, when it required significant software engineering skills to make, to find the minimum over some kind of large database. No, like right now, you just fire up very quickly. Actually, it's fairly streamlined. Many of these services, you can, if you know R, you just instantiate, make an instance with, say, Spark connecting to R, and the R engine works intimately with the corresponding Java components of the Spark framework. They're not exactly Java. Spark is written in Scala, but it is a Java virtual machine-based type of solution. So basically, whatever. But you can actually do lots of stuff in in this way with R and Spark. There's another solution called H2O. I'm not sure. I don't think there's time to discuss it, but it's equally strong, equally good. What I would like to mention is because R is a lazy evaluation language, this actually fits fairly well. The whole workflow, and maybe I should be a little bit, less hand waving and more showing examples. The whole workflow of doing things with Spark actually kind of makes sense with Spark. So let me do this, I guess. So, I mean, you can see here that I loaded the Spark library. After the Spark library has been loaded, I have some separate drive for data which I don't want to keep on my laptop. So basically, I'm telling Spark right now, this read JSON, this SQL context was created up here with Spark. So this SQL context is basically triggering some point at the Spark side to ingest data. And I'm saying, look, read this JSON file. And now when I have this JSON file read across the different processors and etc., I can actually make certain commands like this. So these commands, they're not executed immediately. You actually need to use this command collect. So basically, until this point here, so I start with a certain data frame, this data frame which I prepared earlier. I took some representative. You can see that I have really big data, so I took a very small sample of it. Hopefully it's representative, but that's actually beside the point right now. So I'm grouping the points in this sample. Then I'm making the summarization. Then when I say the command collect, this triggers the querying across all the processes and gives the information back to you. Fairly trivial if you think about it. Obviously used in MapReduce. Hadoop is just one command in Mathematica called parallel combine. Does all this. Now, I mean, you can also see it in SQL. SQL being a functional language, when you have group by having all this kind of when you have select whatever from whatever table, then you have group by and where. This is what is happening here. It's just the functionality is being implemented in a different way across this Spark architecture and so forth using R. So R is intimately connected on each of the Spark nodes with the whatever Spark counterpart, and this is happening there. Great. I mean, I wouldn't say it has been there for a while, maybe for at least 2-3 years. It is very streamlined at this point. As I say, it's almost, it's fairly quick, fairly easy to use it. If I go back to mind map, I do actually have a couple of links here. Like there's, I mean, if you want to learn more about it, I'm going to, basically, this mind map has lots of links published, so you can actually look at the guide here and kind of see, you can see more how you can use Spark. All right, so I mean, I think I mentioned enough about this. So since Oliver Koenig said he mentioned something about using dynamic interfaces over PDEs. Yeah, I assume he is right, but actually, this is kind of, it's not something you do in R. 10 minutes, all right. It's not something you do in R often, but you actually, yeah, okay, so I'm going to skip this example. But basically, you can, this is something I actually demonstrated last year. You have an interactive interface for what is happening. I would actually want to show you the geomapping feature. And this kind of illustrates certain things. Let me see here. So I'm going to quit this session. This is actually another thing which is relatively new in RStudio. You can open multiple sessions for different projects. So I'm going to open this Yelp API project. And so presumably this would load quickly enough. And so if I run this, basically I need to have some, I'm sorry. You need to have like the web API, so Yelp API keys, you need to set up the security and stuff like that. So what would happen here, yeah, let's see actually. I mean, this might be producing some interesting map. Yeah, you know. For those from the Miami area, you know, yeah, well, this is Miami Beach. And in this particular project, we're interested in bus in Miami Beach, because this is actually what people are doing, presumably there. So yeah, they're basically mapped here. Again, you know, like, all right, fine. I mean, whatever. My point is definitely not as fancy, as good as what is in Mathematica, not as consistent. In a sense, you need to go for quite a lot of hoops to do that. You need to figure out how to parse the data from Yelp and so forth. I cannot do this by myself. Somebody else actually has been done this work. But to some extent, this is the other advantage of R. Mathematica suffers of something called the Lisp curse, and I really hope I can actually find this. Well, it's a fairly old article which basically says, look, I mean, because Lisp is so consistent, and so if you're bright enough, you can go so far with it. There's basically just not much documentation about it. I mean, there's no, people who use Lisp, they don't need much help. They can actually do lots of stuff you know, by themselves. Now, this is something similar to with Mathematica. I mean, yeah, we obviously discuss things in Stack Exchange, etc. But R has been it has been always difficult to do stuff in R. So basically, there are lots of help. I mean, if you have any kind of question, you know, about how to do something with R, already has been answered. Invariably, you know. And so basically, this is what was happening with this particular, you know, like when I was doing with Yelp and etc. Yeah, I mean, it was kind of about, again, gathering the data, gathering the access, figuring out what's going on. You need to be in command of it, but I already read somebody, you know, like what somebody wrote about this kind of things, how to deal with it. I do have a little bit, let me see. Actually, yeah, don't save. Let me see here. Maybe you can make chatbots with R. Nobody else does it probably except me, but you can actually program, you can do functional parsers and etc. with R. This, unfortunately, because GitHub is down, I cannot show you this. But basically, this functional, I have written a bunch of functional parsers in functionalities in Mathematica, which hopefully I can demonstrate quickly enough within 5 minutes. Yeah. So basically, with this tool, this functional parsers tool, you can create relatively easily domain-specific languages. And so here you can see like some language about food loving, how you specify it in the extended Bacchus-Nur form, and you can actually, you know, do something like, you can produce some kind of conversational engine type functionality with it. Basically, this natural language has been parsed to this Mathematica expression, and now you need to provide hooks for love food and love type and whatnot, and then produce, you know, the actual result. And you see, this is actually what is happening here. This implementation here in Mathematica just provides implementations for love objects, love calories, and when I call block for love food to be with love food calories and love objects to be love objects calories, basically what you see here is being converted into this dialog expression. So this actually, as I said, this can be done in Mathematica. In R. And I'm going to hopefully demonstrate this within the next 4 minutes, which I don't see easily happening. Just a moment, I'll do this fairly quickly. Yeah, let's see So basically, this language, very similar. It's a different type of grammar, but basically, if I run this code, it should. Yeah, okay. I have written the parsers to a large degree. You can see that, say, this stream here, which is from this string, if you look at what it is here, this is basically character by character breakdown of this. And so now, at this point, I mean, I can do, because this is a Bacchus-Naur form of the grammar, I can run this parser, and basically all the rules have been parsed. So now I need to have the automatic generation of the parsers because I parsed the grammar. So this is basically, I'm very close to implementing a similar functionality now to make conversational engines. I was doing conversational engines 3 years ago for Panasonic Automotive Systems America. It's really lots of fun. It is definitely doable now. I'm using something called monadic parsers. If you look further into these codes in the links I have provided, you'll see that actually, and this is how I'll finish this talk, you'll see that actually you can program the infix operators. I have some much longer, I have these descriptive names like Mathematica style descriptive names of parsers and parser combiners. And this actually here, makes these combinations. And then, I have shorter names and so forth. And right, so basically the parsing is being done. Well, thank you for your attention. I hope this was a useful presentation.